All right, I am super excited to be here. So before we start, can I take a selfie real quick? Let's do that. All right, thanks for letting me record that moment real fast, because I got here and I'm having a blast. This is so cool to be able to learn from the presentations yesterday. Really fascinating stuff. Got me outside of my comfort zone, which is always what I strive to do when I go to a conference. And then the city as well. Obviously, it's beautiful. So really great to be here. Let's get started. All right, so I am a reverse engineer at FireEye. I sit kind of on the back end of the company, which means when our incident responders go out there, they do forensics, they chase down attackers, they recover their tools, and our job is to understand, well, how do they work? And then use that intelligence to kind of, well, find more places that they are, understand how to reverse engineer or how to use their network protocols, how to protect ourselves in the future. That's what I'm doing on the back end. And realistically, and I'm not exaggerating here, on a yearly basis, I'm looking at hundreds, but probably more like thousands of malware binaries, okay? And what I've come to realize is that it's important not just to be focused on the current sample that I'm focused on right now. My boss is hammering on my back, you know, come on, finish this, get it done real fast. Not to be focused on this moment right now, but always to be thinking about, well, what don't we know about? How can we expand our knowledge? How can we find more interesting things? You know, I need to take what I'm doing now, generalize it, and use that to find more interesting binaries. For example, you know, there were some presentations yesterday. They were talking about SCADA malware, ICS malware. Definitely a very interesting domain, right? Companies spending billions of dollars on ICS security. But let's take a moment here and think about, publicly, how many ICS malware samples are there publicly discussed? Like 5, maybe? You got Black Energy, you got Stuxnet, you got Triton. I know that was in the news the other day. Like, what else? What else is there? One thing that is interesting, there was malware called IronGate a couple of years ago. That wasn't found during an investigation. It wasn't found during an intrusion. What happened was my buddy was studying obfuscation techniques for compiled Python binaries. So those are like PYC files, you know, optimized Python code. And there's a very few number of people out there that are actually obfuscating the bytecode. And so he said, this is a kind of interesting technique. We never see this in legitimate software. So what happens when we go and start hunting around, seeing else who's using that? Instantly stumbled across IronGate, one of the 5 public malware samples out there targeting ICS systems. It's worthwhile to do. Okay, so here, we're going to focus on shellcode, little less sexy, maybe more sexy. In any case, I see hundreds of these shellcode binaries per year. And so what I've kind of noticed is obviously shellcode, it's never legitimate. It's always malicious. So that's a good differentiator. If I can hunt for shellcode, I know I'm finding malicious code. That's good. Other things that are kind of interesting to me, shellcode is often not just found as standalone binaries, but embedded within other more complex file types. So if I can find shellcode in a Word document, probably also going to find exploits and other interesting features in there too. Pretty interesting to go about. So it's good to find shellcode. How can we do that? In my experience, one thing that I've found that's useful to do is if I can understand the difference between shellcode and legitimate code, the way that it's structured, then I can find it, find new stuff. Okay, so first hex dump of the presentation. We got 2 of these guys here. On the top, we have a PE file. Well understood file format there. MZ header, well understood. When it comes to shellcode, that structure is not there. It's kind of the Wild West. We have very much less to key on. We can't look for magic headers. What do we need to do that? Let's take a step back and understand what are some key differences between shellcode and standalone executable files that run on Windows systems. The first thing that I would point out is the difference of position dependence versus independence. So for a Windows binary, a PE, a DLL, something like that, they're going to rely on the Windows loader to take the file off disk, put it into memory, and prepare for execution. As part of that, the Windows loader is going to ensure that multiple modules, that is DLLs, are not getting loaded into the same place, colliding. If that were about to happen, the loader would fix up the system to ensure there's not memory references colliding with one another. Makes the job of the software developer a lot easier. So practically speaking, what this means, when I look in IDA Pro, for example, this is the beginning of a function here. There's a lot of stuff going on. But right in the middle here, we have a reference to a global variable. Global variable's name is a security cookie. It's part of this anti-exploitation technique. Okay? If I were to navigate to that global variable, this is data that can be referenced by multiple functions, I can see that it contains some weird hexadecimal value. We're not interested in that. What I want to point out, it exists at this single global address on the left here, 569200. Now the code can actually refer to that specific address because then it can assume at that address, whenever it's running, that's where that variable will be. So sure enough, when I look at the disassembly and now it's actually encoded in hex, that global memory address is right there in the data, 00569200. That was the global memory. It's hard-coded right there. In fact, when I look at the hex dump, there it is in the binary. If I were to open my hex editor, I would see that hard-coded value. Okay. From a software development perspective, this is really nice. We can just reference global variables. It's very easy to do. But within shellcode, that's not something we can do. Because in shellcode can make basically no assumptions about where it's running, what the operating environment looks like. It has to do everything itself. That's because during exploitation or however the code actually got on the system, there might have been additional constraints. So we can't assume that it's loaded at a particular address. For example, this is something I see all of the time. It's a stager from Metasploit. PowerShell, as we can see here. Fairly straightforward. Line 1, we have a bunch of raw bytes. That's the shellcode itself. Might be base 64 encoded, something like that. We'll then ask the operating system or the runtime, hey, please give me some memory into which I can put my shellcode and execute it. Make sure that memory is large enough for the shellcode. That's this argument here, allocation size. And then the runtime is going to give us back a memory region that we can write our shellcode in and then execute using create thread. Now, what's interesting for me here is that the return value from virtual alloc could return us a memory region anywhere in memory. It's not at a specific address. We're not guaranteed to know where that is. In fact, we could call virtual alloc many times over and over. It'll give it different return values each time. Therefore, the shellcode that is written and then executed at that memory address, again, has to be able to deal with that situation. Okay. What does that mean? How are we going to deal with that situation in shellcode? And why do we need to do this? The data that we might store in a global variable might be a thing like the C2 address, where we want to connect to receive commands, or maybe how we're going to avoid forensic software on the endpoint. So we're going to need these global variables. So in order to get access to them without using relative addressing, which doesn't really exist on 32-bit Intel, we need to first figure out where is the shellcode executing at runtime, figure out a common anchor point, and then from there, we can kind of reference the code and the configuration that we need access to. Okay, so memory diagram here, we've got shellcode, a bunch of program logic. Our program counter's somewhere in the middle of the program logic in there, and it needs to reference down here. First thing it'll do, figure out how far into the shellcode is the current program counter, and then from there, and that value is going to be constant, known at compile time. Likewise, the delta between the start of the shellcode and the configuration data that it needs is also going to be constant, known at compile time. So in those two steps, we can recover how to access the configuration data. Everyone with me so far? Now, we'll go down even another level. How does this actually look in our disassembly? We'll get to understand why this is important in a moment. But what this typically looks like is one of these two tricks here. The one on the left is what I see most commonly. Because in x86, there is no instruction, fetch the instruction pointer and put it into a register. It doesn't exist. So we have to fall back and use these tricks here. We have call plus 5, relative call, basically allows us to get access to where is the current instruction pointer, those two instructions. For example, I think I pulled this from Metasploit, something like that, one of those projects. It's the start of a function, bunch of stuff going on here, but what I do see, second instruction, call plus 5, pop into a register. I know that means fetch the current instruction counter value, not used in legitimate programs. I think that's weird. What's going on here? Okay, fetch the current instruction, the program counter, and then from there, compute the global anchor point. Here, the compiler seemed to know that the delta between where we're currently executing and the anchor point is hexadecimal 36 bytes. So 36 bytes to the start of our shellcode buffer. And then subsequently, we reference relative to that anchor point the delta to our configuration data. Okay, simple arithmetic here. And then that allows us to reference, I think this is like the C2 address that was going to be used by the shellcode. Cool. I understand under the hood what's going on and why it's happening. But as a reverse engineer and someone who's out there trying to find interesting malware, how can I use this to my advantage? Legitimate software isn't doing this. Shellcode's doing this. Well, one thing that I notice is that these two instructions are interesting to me, and there's only a very few ways to encode them. So this sequence of bytes, E8, 000000, 58, probably never seen in legitimate software. Anytime I come to that conclusion, I say, well, is there some way that I could build maybe a signature or a matching engine to find that sequence, and then go and maybe across VirusTotal, find all malware that does that? Okay. One easy way to do this is to use Yara. Yara is a pattern matching, kind of like a regular expression engine for binary data. It's kind of a lingua franca for binary signatures these days. So I can take what I learned about shellcode and code it as a binary signature and know that this rule is only going to match on code that's fetching the current instruction pointer and then probably using that to access global data. A weird thing. So I was able to develop this rule. Took 5 minutes. I want to go and test it. First thing I do, run it against my local system. How do you think that worked out? Well, when I ran it, a lot of hits. Granted, I am a malware analyst. There's a lot of malware on my system. But if we look at where these hits are, it's in Python, it's in WebEx, it's in Teams. This is not a good rule. Way too many false positives. We're going to need to use a different technique. So this was not a good thing. Let's think about other ways that shellcode differs from legitimate binaries. We have our position, dependence, and independence. We also have the way that shellcode has to interact with the host system. For example, resolving imports, system routines. On a Windows binary, a P file or a DLL, you can again rely on the Windows loader to resolve any dependent DLLs, shared libraries, and the routines needed to interact with the system. For example, creating a file or connecting to an internet site. We can rely on that. One place you may have seen this is if you've ever opened up a PE editor and looked at the import table for a PE file, you'll see a list of routines that are needed to execute the program. For example, here I see a bunch of routines related to the registry, rendering text, and maybe displaying an image. As a forensic analyst, I might look at that and have a hint as to what the binary is doing. But again, with shellcode, we can't make that assumption. There is no standard file format for shellcode, and shellcode doesn't rely on the Windows loader. So that's not going to be there. And yet shellcode still needs to interact with the system to do its job. Drop an additional file or maybe receive a command from a C2 server. So it has to do all of this work manually. It has to bring along its own implementation of what the Windows loader is doing. In practice, this commonly looks like doing memory forensics on itself. It has to find some global structures. It has to follow pointers. It has to use its knowledge of Windows internals to ultimately get access to the single function pointer to maybe create an HTTP request. It's a lot of work. But it's the price you pay for deploying a payload that's written in shellcode. Okay. Well, let's dig into maybe how this works and see if we can figure out better ways of detecting this. From a kind of high level, what we're generally going to see here is we have our shellcode buffer. This is machine code that's running. It's got a program logic here. And that's going to basically have to find global memory structures like the TEB, the PEB, additional linked lists walk through all these memory structures to eventually resolve the DLLs that it needs to do its job, maybe for encrypting data or connecting to the internet. These guys in orange over here on the right, those are additional system DLLs that are loaded into memory. So once the shellcode is able to find these DLLs, well, then it needs to parse the PE file, walk the sections, find the export table. Wow, a lot of steps. But at the end of the day, resolve the function pointer for opening an HTTP request. Life can continue. It's a lot of work. Concretely, under the hood, we're going to dive down even another layer here. In order to walk these structures, we'll have to take the following steps. We'll have to start by using the FS segment, which you can kind of think of as a register that contains a pointer that always goes to this global structure called the thread environment block, metadata about the currently executing thread. That data structure is pointed to the PEB, metadata about the current process, which has a pointer at offset hexadecimal C, to another data structure called the loader data, which has a number of pointers to various linked lists of DLLs that are loaded on the system. Like I said, it's a lot of work to kind of go through this process. But what's interesting to me as the malware analyst who wants to find more malware is that this is the way you have to do it. And if we know that code has to do this, I'm starting to see patterns. I know that the way they do this, they have to follow this pointer. They have to follow that pointer. They have to follow that pointer. Okay? If that's the case, I wonder, what does the C code look like to do that? It has to look like what we see at the top there. Okay, there's probably some more casting, and the compiler is going to get angry. But like, that's what it looks like. A bunch of pointer dereferences to hard-coded constants. At the assembly level, it's just 3 instructions. Fetching from the FS register, offset 30, then offset hexadecimal C, offset hexadecimal C. When I know that there's a sequence of assembly instructions that I'm only going to find in shellcode, then I start thinking, is there a way that I can code this in a binary signature and allow me to match across various file types? Let's find out. This one's not as easy as the last example, though. You guys can do it. You guys can hang in there, though. No big deal. We'll start with the first term, referencing FS30. I played with Keystone, I think it was, and Capstone, disassemblers and assemblers, to kind of come up with this pattern. But typically, it'll look like the byte pattern 64A13000, blah, 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 blah. Don't memorize it. I'll share a reference later. That's for this first term. Then we'll want to see this offset, a dereference from offset hexadecimal 30. Okay, that, at the end of the day, I apologize, it's so low at the bottom here, looks like the pattern 8B, wildcard, hexadecimal C. All right. And then that third pointer dereference, it could go to one of possible 3 different pointers there. There's kind of 3 options, offset C, offset 14, or offset 1C. Cool. We can again encode that part of the rule fragment as 8B, wildcard, and then one of 3 options. Neat. I've taken my x86, I know what it does, and I've translated that into Yara. A shortened version of the Yara rule is something like this. And the only thing that's really different here is I've added a bit of padding in between the instructions to allow the compiler to potentially reorder some surrounding instructions. Gives me a little bit of leeway. It's definitely not human readable, but I've told you what it does. You can go out on GitHub. You can email me after the class. Happy to share this rule with you. But it looks something like this. Well, do we think this one's going to work? The last one didn't work. How about this one? This one does a lot better. First thing I did, I ran it against my host system. I said, what on my system matches this rule? Oh, there's a lot of hits. But it's not as many as last time. And in fact, when I look at what the hits are, it's not different file types. It's not all over the place. It's actually just my virtual machine images that I use when doing malware analysis. So I'm really only matching the malware that I knew that was on the system. That's good. Now that I know that it works on my system, I cast a wider net. I ran it against one of our malware repositories, fetched, it had about 1,200 hits, which is reasonable against a corpus of like 30 million. False positive rate maybe is not so high there. And then, I double checked what do some of those things look like. And we see here a couple complex functions. This is one complex function. See a number of nested loops and if statements. We don't care about that right now. What we do care about is right at the start of the function, we see that pattern that we're looking for. FS30, offset C, offset 14. It's parsing through the PEB, the TEB, loader data to resolve imports. This is malicious. This is not legitimate. Another example looks very similar. The function is different on the whole, what the program's doing, but it has this snippet of malicious behavior. So this is really good. I'm feeling happy about this. So then I say, from a high level, what are all the files that I found and how do they distribute? Like what kind of data is in there? And this is fascinating. These are the file types that the rule was matching on. Number one entry, raw binary data. That's the shellcode buffer that was extracted. Look at what the number two hit is. Word document. Shellcode in Word document. I bet there's exploits in 300 documents there. Cool. We also see additional Word documents, zip archives, PCAPs, network traffic. Whoa, awesome. Flash data. Maybe there's a Macromedia Flash exploit in there. This is awesome. I thought this was so cool. We took an idea that we thought could possibly work, and we're demonstrating it's matching many different file types that we now know are going to be very, very interesting. Cool. So let's take one of these kind of unusual file types. I took one of the PCAPs. I said, I don't normally deal with PCAPs. Let's see what's in there. It's a PCAP, I promise you. I opened it up in Wireshark. What I see in Wireshark, there's some HTTP traffic in there and some additional stuff going on. But when I see HTTP, I right-click, I do follow stream, and I see the data that's flowing between the server and the client. This is what I saw flowing to the client. And my jaw dropped. I was like, oh, geez, this is not good. What's not good about this? Well, it's HTTP traffic, 200 OK, no big deal. Then we've got HTML. I know HTML. I'm a web guru. I'm not, but whatever. I can parse this. There's JavaScript in here, but it's not normal JavaScript. This is like super obfuscated JavaScript with multiple different kind of obfuscation layers going on. Really weird what's happening here. I thought it was malicious. I've confirmed it's malicious. What's going on here? I continue scrolling through the dump, the traffic of network data. I see this binary blob. Doesn't even look like JavaScript anymore. It looks like raw binary data. Embedded within that is actually those bytes that I was looking for, right at the top of one of these streams. So that's where my match for what I think shellcode should be. Open up this little buffer here in IDA Pro, and there it is. We have the start of a function, we have function prologue here, and then we have parsing through the TEB, PEB, loader data, resolving imports. This is definitely shellcode. It's doing something bad. Pulled it out of the network traffic. Cool. What is it doing? I start pivoting. I look on Google. Where did this come from? OK, it's Metasploit. There's way too much Metasploit in the world. But at least I'm able to trace it back here. Someone's using Metasploit. Specifically, what they appear to... I poke around the Metasploit a little bit further, and I recognize that not only did I find JavaScript in our stream and shellcode on the stream, I also look at this. Magic header down there. It's a PE file in the stream as well. So we've got this whole like layer upon layer upon layer of what's going on in this attack. JavaScript, passing shellcode. The purpose of the shellcode is to download an additional PE file, do reflective loading on that, and it does something. This is a really neat attack here. So I extract that file. I'm pretty sure that's where the payload is. Maybe this is state-sponsored backdoor. So I upload it to VirusTotal. Just code. I didn't actually do that. But reverse engineered it. It's just calc.exe, the legitimate calc.exe. That's how I know real hacking is going on. When I see calc pop up, I've been exploited, right? Whew. But while this might be a little bit disappointing, not state-sponsored activity, it is interesting, and it validates our approach here. This type of rule can work. So what do? Push to production. You know, just throw it out there, see what happens. And so we deploy it across our thousands of sensors around the world. And we've been running this now for months and months and months. And we've had 8 false positives, which is stunning. This is a very good rule. All of those false positives are found within MSDN. And strangely enough, in their RPC code, we see for some reason, I know it's a little bit small here, they parse the TEB, the PEB, the loader data. They start walking around, and then they pass that data to a reg get value. They look into the registry for something that they manually parsed from these data structures. I don't know why it's doing this. It's strange to me. The takeaway, though, is with 8 false positives, we can deploy it even more widely. So we've pushed this out in kind of non-blocking mode across our FireEye devices around the world. And since January, we've seen 500 hits, true positive hits, at our clients for this type of technique, things that wouldn't have been caught by other signatures. Neat. We're seeing fairly good distribution across different matching engines. So both on the endpoint, network data, email data, the rules are working pretty well. And then on the right-hand side here, we can see interesting kind of targeting trending there. I won't go into more detail, but we see a lot of people in education transmitting these types of bytes. My suspicion there is probably a college student who's hosting Metasploit to get his professors or something like that. I don't know. But I'm feeling pretty good about this. This was pretty cool. Now, one of the problems that I have is now I have too much malware to analyze. And one of the things about Shellcode is that it's not always as easy to analyze as traditional Windows PE files, because now I have to know more about what is the runtime it brought along, why is it doing these tricks. It can be kind of annoying. One of the things that's annoying to me is this technique that's commonly used by Shellcode of resolving imports not by the import name, but by hash. Because Shellcode has an OPSEC problem. As a forensic analyst, if I find a file and I run strings on the file, I can see the human readable data within that file. And if we're resolving the routines that we need to execute, create file, HTTP open, and they're sitting in the strings, I immediately know probably what the thing is doing. It's a backdoor, it's a download, or something like that. Shellcode authors know this. They can't embed those strings in plain text. Likewise, in the scheme of things, Shellcode is often a fairly small buffer, especially when it's an exploit or something like that. We don't have kilobytes and kilobytes of space to waste on the names of routines that we need to resolve. So a clever trick that Shellcode authors can use is to encode the routines that they need to resolve as hashes, fixed length hashes, often 2 or 4 bytes long. So what this means, so when we run strings, we don't get anything useful from shellcode buffers. Now the way that this will work, we've talked about these memory structures and these pointers that need to be followed. That stays the same. What's different is that by the time we get to win_http.dll and we are walking the export table, looking for functions that we need, like open or close, rather than doing a string compare, instead, we have an embedded list of hashes that we're going to look for. Maybe this is CRC32 or a rotate right scheme. We have a list of hashes that we need. We can hash each one of the entries in the export table and then search for a match. And then from there, we have our function pointer. What this means as a reverse engineer is that I'm a little bit more out of luck. Because I can open this thing in IDA Pro, I can disassemble it, but when I look at the results, I see a lot of these really random looking values and none of the routines that I'm used to seeing in IDA Pro. I'd love to see create file here. Instead, I have this thing and I don't know what that means. In order to understand what does that number mean and what routine is being invoked, I have to reverse engineer the hashing routine, do a brute force attack, and it's really annoying. Fortunately, a lot of these shellcode frameworks have either been leaked or published open source online. And so there is a pretty good corpus out there of what shellcode uses and what hashes they've picked. We can take these routines. For example, here's Metasploit, found it on GitHub. I can take a look at their hashing routine. It's right up there. Anyone can look at it. And we see that the way that this hashing routine works is it's a bitwise rotate right by 13 bits at a time. We'll take a character, rotate it, XOR it with the next character, rotate it, XOR it with the next character. Bye. I can re-implement this in Python, and that's what we've done on the Flare team. We've basically taken every shellcode hashing routine that we've seen in the wild, we've re-implemented it in Python, and used that to create a database of all possible hashes that we've seen in the public. What this means is that you can download this database. It's a SQLite database on GitHub. You can download it. You can query it. And you can say, hey, for a particular hashing routine, I have this value. What does that value resolve to? So as a reverse engineer, when I'm looking in IDA Pro and I see this really weird number here, I can simply query the SQLite database and say, what does that value correspond to? That weird number corresponds to the symbol name Internet Open. And I can script this. I can do this very quickly. I can update my disassembly listing and have a higher level understanding of what this function's doing. My job's easier. This is still better than where we were a couple years ago when I'd have to do this all by hand. Other techniques for doing this by hand might involve maybe setting a breakpoint on this instruction, debugging it until there, and then resolving what routine we're about to recall. It's a very manual, annoying process. I can use this brute force attack. That's cool. But again, one of the issues is I have to manually transcribe what I see in the assembly and transcribe that, import that into Python, and ensure that it's a one-to-one match. That takes a long time. It might take hours. I don't really care about the implementation details. I don't want to do that. I want to understand, what is the C2 protocol? Where is it connecting to? Who's behind this? What's the attribution? So I'd still really like to avoid this manual implementation of hashing routines. Ugh. One way that we can do this, well, you can sometimes Google for these things. But I'd like to present one way that we can actually do a lot of this automatically. And this is going to be an automated hash decoding, a reversal of the hash. There's kind of two things I hate in dealing with malware. I mean, I like them. I think they're technically interesting, but I have to do it so much that it's boring to me. The first is automatic string decoding. A lot of malware obfuscates its strings using XOR routines and things like that. It's really tedious to analyze. Developed a tool for dealing with that. It's called Floss. It'll automatically deobfuscate strings for you. Really easy to use. You should use it on every investigation. Okay, that's a solved problem. What isn't yet a solved problem is this automated hash resolving. I still have to do this manually every time. What's interesting to me, though, is that these two problems are very similar. Both of them are super tedious to do. They involve routines that have a lot of looping. They look kind of unusual. They look like encryption routines. That means I can usually automatically identify them. And they're also typically like referentially transparent, which is just a nice computer science-y way of saying they're easy to understand. What that means that I can do is put together a script. Let's see if this works here. A script, oh, sorry, I see what's happening. A script that can run against shellcode that I don't completely understand, that I haven't manually marked up. That's in this, for example, metasploit.binary here. It's just a raw shellcode buffer. I have a Python script and a couple system DLLs in the same directory. That's where I think the shellcode is going to be resolving routines from. I can run my Python script. It's going to load the Metasploit binary into memory, and it's going to use a CPU emulator, which is kind of like a virtual CPU. It's a fake CPU, and it's a CPU that we can interact with programmatically. Just set up an execution environment, load Metasploit, load some additional DLLs, and then we're just going to let the shellcode run. And using some tricks, it's going to take just a moment here. It's going to emulate the shellcode, identify what are the hashes that the shellcode is going to use and need and be searching for, and then it's going to automatically resolve what those hashes are to the symbols. And it's doing this all automatically without me having to go in there manually. This is really helpful, really useful. In the last couple minutes here, I'll walk through how this works. Okay, so in 15 seconds, I've saved hours of work. Useful. So how does this work? Under the hood, we've kind of touched on this a couple times. We know that the shellcode will walk the TEB, the PEB, the loader data to recover the DLLs that are loaded into memory. It'll enumerate each of those DLLs, enumerate all the exports in those DLLs. We'll hash each of those entries, and if the hash matches what we're looking for, then we can return that symbol and call it directly. So for example, we might be enumerating DLLs like kernel 32 or win inet. And then for each one of those, the exports might look like something, create file, delete file, and each of those is going to, when hashed, resolve to strange numbers. Now in code, this is actually a lot more complex when it's an x86. We see a bunch of nested loops here. But the key instruction out of all of this is this comparison here. When we're comparing our hash against the wanted hash. We don't quite know how this hash algorithm looks like. We haven't reversed that. But this one comparison here is key to our understanding. It's actually this instruction right in the middle here. Comparison between two registers, the computed hash against the query hash. So the way that we can set up our emulator is this, to exploit this. We'll map in our shellcode into the virtual CPU's memory. We'll set up the memory structures to emulate, to look like things that are like the TEB, the PEB, and the loader data. We'll put our DLLs into memory so that they look as they would in the real world. We'll set up all the pointers correctly. And then we're going to emulate the shellcode. We're going to let it run until we see that it's actually accessing those structures. Then we know it's trying to resolve routines. At that point, what we're going to do is that one instruction that does the comparison, we're going to basically we're going to do a taint on that instruction, on the data being compared in that comparison. Because we know that on one side we have the computed hash for a symbol that we know that's in an export table, and on the other hand we have this thing we don't know what it is. That's what the shellcode's looking for. Now, we can do that taint. We can say this is a value that we're looking for. We're in kernel 32. We've enumerated the exports. We're looking at create file. That's the human readable symbol there. And then what we see here is the tainted value here doesn't really matter, but the malware has computed a hash, and therefore we know create file hashes down to this value here, 1, 2, 3, 4, 5, 6, 7, 8. Interesting. Then what we can do is say, what are all of the values seen on this side here? And we create a list. And now we see, OK, delete file. That's over here. 9 A, B, C, D, E, F, 0. And we create a big list of all the hash values seen on this side of the expression. That's going to be tens of thousands of entries. Now we can take a step back. We can take each one of those entries, and then we can rerun the resolution routine, providing the entries from that list to the resolution. We can go back and say, oh, I saw that the malware, it was looking for a create file. I saw that the hash that it had generated was 1, 2, 3, 4, 5, 6, 7, 8. Now, I'll let the malware go and run, do its resolution routine. I don't really care how this whole thing works down here. I just know that the purpose is to resolve that strange, complex number into this human readable symbol. Awesome. And so I can work my way through the list of 10,000 entries and just let the malware do the work for me. I actually don't really know what it's doing. I don't care what it's doing. All I care about is it's resolving these shellcode hashes. I don't have to do that work. So I thought that was kind of interesting. At this point, just a couple minutes over. It's probably a good time to answer any questions, or maybe even move on to the additional presenters today.